All right, we'll go ahead and get started now. Hi, my name is Bryan Hughes. I am Nebrius on GitHub, Twitter, and basically everywhere on social media. And I'm a technical evangelist at Microsoft. I've also been a Node user for a really long time. I first started using Node back in 2011 in the days of 0.4. And I've been doing a combination of that and web development ever since. And for a while, I was actually a leader of the Node.js project as well. I was on the Technical Steering Committee, and I also chaired another committee called the Community Committee. And so today, I'm going to talk about a topic that is kind of an intermediate to advanced topic, but I'm also trying to make it really accessible. So I think if you've not used Node before, this should also work. So real quick, though, a show of hands. How many of you have actually written a Node.js application before? Right, so OK, most of you, a few people who are new to Node as well. That's totally fine in this one. So with this talk, we're going to be talking about the Node.js Event Loop. Specifically, we're going to be talking about how asynchronous methods in JavaScript, or in Node.js specifically, work, and how that has implications for performance, specifically around multi-threading. But before we go into that, I want to kind of give just a quick overview, hopefully review for many of you, about what multitasking actually is. It turns out there's a bit of a history to multitasking. And kind of knowing that history, I think, really helps to crystallize some of the concepts and why we are where we are, and also why Node.js made some of the choices that it made in its design process. So in the personal computing world, if we go way back in time, we only had a single process. Think about the days of MS-DOS and the original Apple computers before the days of the Mac. In these systems, the way they would work is you would first boot up the operating system, DOS, which in those days was really just an application like any other. And then inside of DOS, whenever you wanted to run an application, DOS would more or less unload itself and then load that application up. DOS would actually stop running when you're running your application. Inside of that application, it could only do one thing at a time. There was no concept of having two or more programs run at once. And that's just kind of the world we came from. Same thing on the Apple side. But of course, we quickly realized that we wanted the ability to do more than one thing at a time. This is a super useful thing to have. So the next thing we created was this thing called cooperative multitasking. And this actually worked pretty well, especially at the time. We started to see this in the days of Windows. This is one of the big things that Windows brought along. And this is also one of the big things that the original Mac OS has brought along, before the days of Mac OS 10. And so the way cooperative multitasking works is we have an application. It's sort of running along, doing its thing. And whenever it's at a good point in time to stop, the application will actually call a method that will tell the operating system that, OK, I can go ahead and pause now, and we can run something else. Typically, this would happen in the form of a C function called yield. So you have an application that's running along. It'll hit this yield call. We'll transfer back over to the operating system. The operating system would load itself back up again. And then it would call out to another program. And then that other program would kind of run along and keep going and going until that application called yield. And they would be able to switch back and forth. And it would feel like we were running more than one program at a time, even though in practice we actually weren't. In computing up until relatively recently, we could only actually run one set of instructions at a time, because the hardware in these systems only had one processor. And so if you have one processor, you can only do one thing at a time. But we were able to fake it, and cooperative multitasking was the first attempt. But there's a pretty big kind of drawback to using cooperative multitasking, which you may have realized already. And that big problem is that it's up to the application to call yield. So what if that application doesn't call yield? Let's say there's a bug in your application or something like that. You get caught in an infinite loop or whatever. Well, that application is just going to keep running and running and running forever, and it will block not only that one application, especially if it's a bug, but it'll actually take down your entire system with it, because it won't allow anything else to run. And so in the Windows world, this was actually the case for Windows 3.1, 95, 98, and ME. Windows had this problem all the way up until 2001, as it turns out. Same thing in the Mac world. Mac OS, from Mac OS 1 all the way up to Mac OS 9 had this exact same problem. So you might remember the days back in Windows 95 and 98. You have an application that will crash. You could take the window and drag it around on the screen, and you get this huge ghosting thing. And this is actually exactly why. It's because the application was never able to let Windows itself run, so it could go and redraw itself. So this is kind of a limitation. Applications have bugs. This is just kind of the state of the world. But we don't want an application bug to take down our operating system. So another variant was created, and this is called preemptive multitasking. And so preemptive multitasking had been around for a really long time in like the server mainframe supercomputer world and in the Unix world, but it's kind of a new thing for personal computing. So with preemptive multitasking, it works a little bit differently. Instead of having the application tell the operating system whenever it's okay to pause the application, the operating system actually will schedule like a timeout, an interrupt actually at the hardware level, and it will automatically start running, and it'll pause the application on its own. And it'll take the application state, all of the data that's in the registers in the CPU, all that low-level memory, and it'll actually save it somewhere else. So it'll pause it, save its state, put it to the side, and allow something else to run. It'll run it a little bit, pause it, save its state, and we can switch back and forth like this. So we get the same effect where we're still only running one thing at a time, but now this is managed completely by the operating system under the hood. So if an application starts misbehaving, it won't take down the rest of the operating system. So this is a huge improvement. On the Windows side, this was first introduced with the NT kernel. Specifically, there was NT, I think 3.1, 3.2, something like that was the first. But we really first saw this with NT4, which gained a lot of traction in the business world. And this was one of the key reasons for it, is a misbehaving application couldn't take down the rest of your system, so you are more productive. And so there was NT4, and then Windows 2000 has also had this kernel. And then most importantly, Windows XP had this kernel as well. So they actually took this business kernel and moved it over to the consumer side because it gave a much better user experience. And so once we got to Windows XP, we had preemptive multitasking in Windows. And there's a very similar story on the Apple side as well. Whenever Mac OS X came out, which is a ground-up rewrite for 10.0, they, instead of using the old kernel, which was a custom kernel, they actually switched to using a variant of the FreeBSD kernel, so from the Unix world. And so Apple got preemptive multitasking that way. And so once we had that, both of these systems, once they got through their first early iterations, were considerably more stable than the previous ones, and oftentimes a lot faster, as it turned out. But it turns out we could actually take this even further. In 2005, we got the first multi-core CPU. So at this point, we actually had hardware support for running more than one program at a time. And so this time, hardware researchers and software researchers started getting together and saying, how can we work together to improve parallel performance even more? And so we created this thing called symmetric multithreading, which Intel, by the way, has branded as hyperthreading. So if you've heard of hyperthreading, that's symmetric multithreading. AMD has a variant as well, as do, I believe, some of the ARM chips, although I'm not certain on that. And so with symmetric multithreading, what happens here is that the OS is actually able to send some special assembly instructions into the processor that can help to inform how work is being done. And so the processor is actually able to optimize when we have these two sets of instructions that the processor or the operating system knows comes from separate threads. Therefore, they're not dependent on each other in any way. And the CPU can kind of optimize around that. So inside of a single core, inside of a CPU, a single instruction, an assembly instruction, is actually broken down into steps, and it executes these in a series of steps that run in order. And this is called a pipeline. Or, well, sometimes in order, there's optimizations around that too, but we won't go into CPU architecture too much today. But so inside of the CPU core, in each of these stages, there's usually multiple copies of hardware. So if you want to do, take two floating point numbers, you want to multiply them together, there's a special piece of hardware to do that, called an FPU, or floating point unit. But in processors, they actually have a couple of them sitting side by side. So this is not a complete separate CPU. It's only a couple of little parts here and there are separate. But they're there, and these instructions can take advantage of that. And so depending on your code, you'll see a performance improvement of anywhere from, well, 0%, no improvement, which happens, but up to usually 15 to 20%. It's not much, but it's something, and it helps. And so by marrying these two together, we're able to get a better performance out of our multi-threaded code. And so all the modern operating systems today support this, as do a lot of modern processors. And so this is kind of where we're at now. Now you might notice, though, I actually did a little bit of a switch in terminology. First I was talking about cooperative multitasking, and then preemptive multitasking, but then I mentioned symmetric multi-threading. Well, it turns out there is actually a difference between them. And so whenever we say a task, also sometimes we say process. Processes and tasks are the same thing. Task is kind of a generic term, whereas process is a little more technical inside the kernel, but they're basically the same thing. But threads actually are very different. So a process is kind of like a top-level container. We can think of this like an application. Technically, applications can have more than one process, although this is not super common. But a process is a very self-contained kind of thing that runs independently on its own. One of the key traits of a process is that it has its own memory space. So whenever the operating system launches a process, it's going to like carve out a chunk of memory just for that application. And no other process can access that, unless there is a bug in the operating system which could allow that, which, by the way, this is how a lot of viruses work, actually. Like, fundamentally, viruses work by trying to break out of their own memory process and take over someone else's. But if we're not a virus, and I hope none of you are virus writers, then we're all going to be working inside of one memory space for our process, and we can't access any others. So this means if we do have one of those applications that has more than one process, or if we want to talk to a different application, then we have to like cross this boundary. And there's no built-in way to do that, so we have to use a thing called inter-process communication. Now, this is a generic term as well. This is not a specific technology. Typically, IPC is done using some form of socket. Sometimes this can be a TCP/IP socket, but in the Unix world, this is often a Unix domain socket. Pretty similar in a lot of ways, less overhead. Technical details we can go into, not really important. But the key thing that is similar between a Unix domain socket and a TCP socket for this case is that we are serializing a message and then sending it across a virtual wire we can think of. So if we think about networking, we can't just send anything out. We have to basically turn it into a string or a buffer. We can't send like a function over the wire or like an object instance. We have to do what's called marshalling. And this is a computational process. In the JavaScript world, we can think of JSON.stringify as the typical method. This is typically what we use. But we have to like call some code. We have to do some work to convert whatever our data is into something that can be transported. And this takes time and also memory. And then once it's sent across this communication mechanism, then we have to do the reverse case, which also takes time and memory. Threads are very different, though. So a thread always runs inside of a process. A process, it can spin up as many threads as it wants. And there's always this like direct correlation. A process is kind of like a parent of a thread, is how I like to think of it. And one of the key things that's different is because these threads run inside of a process instead of in multiple separate processes, they have access to the same memory. So this means that a global variable declared in one thread can be directly read by another thread. We don't have to do this like communication. We don't have to package our data up and send it anywhere. We can just read it. And so this is really great because there's no performance impact. It's very, very fast. But there is a bit of a problem, especially on modern hardware. These threads can be running at the same time, and it's possible that they're even running a separate core, so they're like actually executing instructions at exactly the same time. So let's take an example where we have two threads, thread A and B. So thread A writes to a global variable, and then thread B reads from that global variable. So what is the result going to be if these happen at roughly the same time? The answer is it depends. You might run your application the first time, and thread A will write to that variable first, and thread B will read from it. So thread B will get whatever value thread A wrote to it. But the second time you run it, like on the exact same code, exact same machine, perhaps just a couple seconds later, and the reverse happens. Thread B will read from that variable before thread A gets a chance to write to it. So you actually get a different answer each time you run it, and that's a bug. Specifically, that's a type of bug called a race condition. And so if we want to avoid these kind of bugs, we have to actually write code ourselves to make sure that these things are orchestrated. Usually we have to tell one thread to sort of like just kind of like wait and hold up a second until work in another thread is done. And there's a lot of different mechanisms to do this. It varies from language to language, runtime to runtime, and most of these even have multiple mechanisms inside of themselves. But they all kind of have the same theme of like slowing down threads and scheduling them so that they can work together. And this works really well, except that it's actually really hard to program. In any reasonably complex app, writing these multi-threaded code tends to be very, very bug-prone, even for really experienced developers. And it actually turns out that this is kind of like the cooperative multitasking model. Like those same issues that affected cooperative multitasking, or similar issues, affect us here. Specifically that, anytime we are reliant on the developers getting it correct, there's going to be, an error rate. We all write bugs in our code. So if we can have a way to manage this, this makes things a little easier. And a bunch of different people in different languages and frameworks and all that have been experimenting with ways to make this model a little bit easier. Apple has Grand Central Dispatch, for example. And Node.js has its own very specific answer to this. Being a new framework, it had a chance to look at everything that had been done over the last 20 years or so in multi-threading and say, how can we make this easier and less error-prone? And so its answer was, we're just not even going to bother. We're just not even going to give you threading primitives at all. And so Node.js is single-threaded. This is a thing that we say all the time. The reality is a little bit more complicated, though. I like to say Node.js is single-threaded, except when it's not. So whenever I talk about this, kind of what I mean is all of your JavaScript, like every single JavaScript file that either you wrote or is in a module that you're using from some other author, or inside of Node.js itself. Node.js has a lot of JavaScript built into it. And so all of that JavaScript, in addition to V8 itself, V8 is the JavaScript engine that runs inside of Node.js, but also the event loop, these all run in a single thread, which we typically call the main thread. And so when we say JavaScript is single-threaded, this is really what we're talking about. It's like all of these things run in one thread, and there's no option to run it in a different thread. Things get a little bit more complicated in the C++ world. So in the Node.js code base, last time I checked, is about 2/3 JavaScript and 1/3 C++, give or take. And so C++ is different because C++ has access to threads. We actually can use threads here. So inside of JavaScript, all methods are either synchronous or asynchronous. By the way, whenever I say asynchronous, do people know what I'm talking about? Raise your hand if you've worked with asynchronous methods in JavaScript before. Cool. So most of you've probably seen them. So all of the synchronous methods in Node.js, or at least the ones built into Node.js, are pretty much always backed by C++. There's C++ under the hood eventually. It's massaged and manipulated in JavaScript, but eventually we're talking about C++ code being executed. And so if your JavaScript function is synchronous, then that C++ code that's backing it is also run in the main thread synchronously, which kind of makes sense. That's sort of the definition of synchronous. C++-backed asynchronous methods are a little more complicated. Sometimes they do run on the main thread, and sometimes they don't. It actually depends on what that C++ method is and how things are kind of architected under the hood. And so this is kind of what we're going to be focusing on for the rest of the talk, is like how asynchronous methods work and the different mechanisms used to make them actually asynchronous. We're going to do this by looking at a couple of examples. We're going to start by looking at a module built into Node.js called Crypto. The crypto module has a whole bunch of mechanisms for doing all sorts of kinds of cryptography, from hashing to encryption, random number generation, all those kind of things that we want to do with cryptography. And we're going to start with a short method here. This is using a method called pbkdf2sync. pbkdf2 is a hashing algorithm. It's a pretty modern one. So if you're working with usernames and passwords and things like that, and you want to hash it before you put it in your database, this is typically the hashing algorithm that most security researchers are recommending right now. And I specifically chose this because this is a very processor-intensive operation. The whole way hashing works is that we run it through this mathematical algorithm that is, by design, very intensive. And so we're just doing a whole bunch of CPU work. We're basically tying up the CPU whenever we run this method. And so what this code does right here is we are going to actually run this method twice. We're going to hash the phrase secret. We're going to give it a salt. We're going to do 10,000 iterations for a key length of 512 bits. If this doesn't make any sense to you, don't worry about it. It's not really that important for this example. But the key thing is we're running this very CPU-intensive process twice, synchronously. And so when we run this code, we get an execution timeline that looks like this. You can see we run that first method, and once it starts running, it blocks everything else, and it's going to run fully to completion. Once that method is done, then we see that second one start, and it will run to completion as well. And this whole process, to do 2 hashes, took us about 275 milliseconds. So cool. That's what synchronous code is. This is exactly what we expect. Now let's take a look at the asynchronous variant. So we see this code is exactly the same. The only difference is that instead of calling the synchronous version of the method, we call the async. And by the way, in Node.js, anytime we have the option of either calling a synchronous method or an asynchronous method, the synchronous method will have the word sync, S-Y-N-C, at the very end of it. And the asynchronous method does not have that at all. There is no async word to indicate it's async. And so this is the asynchronous method. And what we're timing here is from the time we first call pbkdf2 to the time that callback is called at the very end. So when we run this code, see, we're still doing exactly 2 hashes, but this time asynchronous. We get a timeline execution that looks like this. So you can see these 2 calls. They were asynchronous, and they were actually run in parallel. This is run on this laptop, by the way, so we had 2 cores available. And so they were actually able to run on both cores, and we got a pretty significant speed up. You see it took 125 milliseconds, which is roughly half the time. There's different overhead for sync and async and just different runs, so that explains that little extra bit. We can ignore that. But yeah, so this is actual parallel computation. So you can see we wrote some Node.js code. We ran it in separate threads. We did some parallel computing here without having to write any threading code at all. So that's pretty cool. All right, so let's say we increase this from 2 requests to 4 requests. It's the exact same code. I just changed that little variable for the for loop that said how many times it would run. And we run this 4 times, and we see that they all still run exactly in parallel, but the time increased up to a little under 250 milliseconds. Now, the reason for this is, once again, I ran this code on this laptop. This laptop is a dual-core laptop. It has 2 processors. So since we ran 4 requests, basically what the operating system did, once we kind of worked through the Node.js parts, it took 2 of these and it ran them on 1 core and ran the other 2 on the other core. And when it's running these, it's doing a preemptive multitasking along with symmetric hyperthreading. So it's sort of bouncing back and forth between the 2 threads, doing a little bit at a time. And so because of that, that's why it took longer. This was a fundamental limitation in the hardware itself. All right, so let's keep going on this trend, and let's up it to 6 requests. All right, so this is actually a little more unusual of a graph. This is probably not what we would expect. We get the 4 in parallel, but then we get this weird little tail right here. So I'm going to superimpose it, and we're going to look at all of the results at the same time to show that, indeed, those first 4 ran exactly as the 4 requests did. And then these other 2 took a little longer. If you kind of look at the 2 blue ones when we ran 2 requests, it actually is exactly that same length. So what's going on here? Well, it turns out under the hood, there's a C++ method for doing this kind of hashing algorithm. It's synchronous. C++ has some asynchronous work, but this is not one of them. And so in order to run these in parallel, we had to run them in separate threads. And so Node.js actually will automatically ship this asynchronous work off to a thread in the background. But it doesn't spin up a new thread for each request. Instead, what Node.js does is at the beginning of your app, it will actually spin up 4 threads automatically, and it will just reuse those threads throughout the life of your application. And it calls this set of threads the thread pool. And it just so turns out that the default thread pool size for Node is 4. And that's why we get a tail. What's going on there is we make that very first request, and Node is going to say, OK, we've got this request. I've got these 4 worker threads sitting here. Nothing's being done. So I'm going to ship off that first request to the first thread. Get the second request, ships off to the second thread, the third to the third, 4th to the 4th. But when that 5th request comes in, Node says, oh, hey, all my threads are actually busy right now, and I don't have anywhere to put this. So instead, I'm going to put this request into a queue and wait until one of those 4 threads becomes available. Same thing with that 6th request. And so once the first request finishes, Node is going to pop that 5th request back into that same thread the first was in, assuming the first thread finished first. We're going to hold questions to the end. And yeah, so that's where that tail comes from. It's just because the number of threads were actually blocked. And so this is just kind of a basic nature of Node.js and working with Node.js. By the way, you can actually change the thread pool size. There's just an environment variable you set, and you can set it to whatever you want. All right, so we're going to look at another request. This is a much more real-world request. We're going to look at making an HTTP request. So Node.js is a server-side framework, or at least primarily used for that. And so most Node apps are really concerned with doing some kind of networking work. So we're going to look at this code right here. What this does is we're using the HTTPS module, and we're going to download my profile photo from my personal website. I specifically chose this file, and the reason I'm even telling you all this is because, well, first of all, this file is relatively large. It's about 800 kilobytes, so it takes some time to download. Also, my website is hosted inside of Azure, and Azure has really consistent throughput throughout the entire system. So when we're doing a lot of tests against it, we get repeatable results. And finally, I wanted to do this because I had control over whether or not this is behind a CDN, and I explicitly made sure the CDN was disabled for these requests. Like CDNs are great for serving up websites because they can get assets really close to the user geographically. So download times are faster. It reduces your bandwidth costs, like all of these great things. The one thing it also does, though, is it can make this a lot less predictable and consistent, at least for the terms of benchmarking. So for testing, for this specific type of test, we wanted CDNs disabled. So that's why I'm using it. So we're going to download this photo. We're going to listen for the data event. This is a thing that's necessary in Node. Node does some optimizations. Like if we're not actually going to look at the data that we downloaded, it's actually going to optimize and just skip around it entirely. So we have to tell Node, give us all this data. And so now it's actually going to download everything. And then it's going to send us an end event once we're done downloading the entire body. And so we're going to measure how long this takes from the time that we call https.request to the time that this end event is fired. Now in the HTTP world, these are all asynchronous. There is no synchronous option at all. You can only do an asynchronous request. So we make 2 requests, and we say they took pretty much the exact same amount of time. So this is cool, and this is good. We want to see this kind of consistent type of number. And this whole thing took about 700 milliseconds. Now when we increase this to 4 requests, like we did earlier, we say they all still run in parallel. We also still took about 700 milliseconds. It didn't take any longer. Now the reason for this is that networking is a very different type of load than doing CPU-intensive work. Whenever we're downloading something from the web, and specifically in this case, we're downloading it and putting it into memory. We're not even writing it to disk. We are purely limited by the network. Like most of the time whenever we're running this code, the computer is just sitting there waiting. It's actually not doing anything at all. It's just kind of idling, waiting for a little bit of data to come in, which it'll then process. So because of that, we were not limited by processors. It didn't take longer to do that computational work. So the fact that this is dual core doesn't apply to networking. And so it'll take the same amount of time. Now let's increase this to 6 requests like we did earlier. So this is different. This is behaving really differently than crypto. So when we did this, we can see we did all the requests. They all still took about 700 milliseconds. So it implies that the thread pool isn't doing the same thing here. And the reason for that is inside of Node.js, we try to make use of C++ asynchronous primitives whenever possible. It turns out you can actually do asynchronous programming in C++ as well as in Node.js and in JavaScript. It looks a little bit differently. C++ doesn't quite have the concept of first-class functions. The ability to pass a function as a variable, so it's a little more cumbersome. But basically what we do is we make this request. We actually tell the kernel, this is a kernel-supported feature. We tell the kernel, go ahead and download this file for me. And that's an asynchronous method, so it returns immediately. And then we can actually check into the kernel and say, like, hey, did you finish this thing yet? And we just kind of ask it over and over again, like, hey, did you finish? Hey, did you finish? Hey, did you finish? And eventually it'll say yes. And we'll be like, cool. We'll call some other C++ method that says, get me the result for this operation that you've just said is finished. And so that's asynchronous. And Node will use that whenever possible because the kernel is able to optimize this better than Node can. But also because this is asynchronous, we don't have to run this in a background thread. So these are actually run on the main thread. The reason being is that all of the actual work being done isn't even, not only is it not run in the main thread, it's not even run in the Node process. It's run inside the kernel itself. And so we saw a very, very different result here than we did before. And really kind of what this all comes down to is the performance of a method call in Node.js is going to be dependent on whether it uses a C++ async primitive or whether it has to be thrown into the thread pool. And the thing that manages this inside of Node.js is a thing called the event loop. Now, the event loop does a whole bunch of different things, but I'm only going to talk about one specific part of it, and this is specifically around this whole threading asynchronous thing. And so we can kind of think of the event loop as like a central dispatch. It's called the loop because it actually operates in a loop structure if you look at the data flow. And so whenever we make a request, say we're going to make this HTTPS request, we're going to start off in JavaScript. It's going to go through some various JavaScript methods. We're going to do some like pre-processing work in JavaScript. But eventually, we're going to hop across V8 from the JavaScript world into the C++ world. Once we're inside the C++ world, this gets sent straight into the event loop. And then once we're inside the event loop is going to take a look at this request. First, it's going to say, was this a synchronous request? OK, I'm going to go and call the C++ methods necessary to do this work directly. So this is done inside the event loop, and the event loop's in the same thread as your JavaScript code, and that's what makes it synchronous, because it's actually synchronous all the way through. But then the event loop will also look and say, oh, well, okay, this other request is an asynchronous request. So then the event loop decides, okay, is there a C++ asynchronous primitive that can do this asynchronous work? All right, cool. I'm going to go ahead and send this request off directly to that C++ code. But then if it falls back even further and it says, oh, well, this has to be run in a background thread. We can't do this asynchronously. So it's actually going to put it into this thread pool queue and wait for one of those threads to become available. And then it ships it across to that thread, and it does its work. Now, in all three cases, well, actually, in the two asynchronous cases, kind of in the third case, whenever that work is done, it's going to ship the results of whatever that work was back to the event loop. So you can see we're kind of completed a little over half circle now. So it gets sent back into the event loop, and the event loop will then take that and reroute it back to whoever originated it from. So it's going to go back through C++, it'll hop across V8 back into JavaScript land, and then that side of the node code will then take that result, and it will send that to all of the callbacks that are registered to receive that result, usually in the form of events, sometimes in the form of a callback. And so you can see we have now completed basically like a loop. Now, the event loop does a whole bunch of other things we're not really talking about here, but like it manages timers, it manages when it's time to shut down Node itself because there's no more work to do, and a handful of other things like that. So, of course, the question that then comes up is which APIs use which? It's a little bit complicated, and this is an overview. But basically, this tells us kind of who uses what. For the record, I actually borrowed this slide from a guy named Bert Belder, who actually wrote a good chunk of the event loop itself. So for kernel async, which is the term that we use when we're talking about something that uses a C++ asynchronous primitive, pretty much anything networking based. So any of our TCP and UDP calls, which of course includes HTTP, FTP, and everything else, all of those are done using kernel async. This is also true of pipes. Node.js is based around the concept of streaming, which is pretty similar to how it works in other languages, just a different API kind of structure. But when we have two streams that are connected together, that's called a pipe. And so pipes are also handled inside of the kernel. And then finally, all of the DNS.resolve calls. These are also kernel async. But there are some things that don't have C++ asynchronous primitives. And the big one there is actually the FS module. So all of your file system calls, those are actually run inside of a thread. And typically when you're working with the file system, the speed of your hard drive is going to be your limiting factor. But suppose you have a really, really fast disk system that causes the CPU to get really intense. It is possible for when you're doing a lot of file system I/O to run into this thread pool limitation. DNS.lookup itself, as it turns out, actually doesn't have an asynchronous version, so that's also run inside the thread pool. And then finally, there's a couple of edge cases around pipes, specifically if you have pipes that you're piping from the file system, because the file system itself has to run in threads. Now, those are the common ones. There's a couple of them that vary from operating system to operating system. So on Unix systems, both Mac OS and Linux, as well as FreeBSD and whatnot, Unix domain sockets, the thing I mentioned much earlier that is used for inter-process communication, these are done inside the kernel. All of our TTY input. So TTY input is all of our console logging, things that we're writing to standard out, standard error, standard in. This is a TTY thing. Also, if you happen to have a serial port, say you're working with hardware, IoT kind of things, that is also done using kernel async. And then finally, child process module. So child process is how we can shell out and call other executables. And so all of those are also done using kernel async primitives on Unix. On Windows, though, it's actually a different story. It's kind of the opposite case. Child process, if you want to shell out to another application, that's a blocking call. So that actually has to be run in a background thread. Same thing with TTY input. Reading from the console and things like that is a synchronous call in Windows, so we have to run that in a thread. And finally, there's a couple of edge cases around TCP servers on Windows that have to be handled by the thread pool. And so if you want to learn more about the event loop, there are two really good talks on this. One is by Sam Roberts and Bert Belder, who are both also collaborators on the Node.js project. And they also both worked in the event loop. Their approach to this is that they sort of start from the inside and they talk about how the event loop is written and sort of work their way out, as opposed to us where we sort of worked our way from the outside in. And finally, there's a great blog post by Daniel Kahn who kind of goes and summarizes a lot of this information in blog post form as well. And by the way, I'll put these slides on Twitter as well, so if you don't get the links recorded, you can find it there too. But one more thing. So we've been talking a lot about how Node.js doesn't have threads. Well, that's actually probably going to change in the future. So this pull request was opened pretty recently. This pull request was actually opened on a fork of Node called IO.js, a clever play on a different fork that was called IO.js with the letters IO. And this fork is kind of a place where just a lot of experimentation is happening. You know, there's no guarantee any of this will land, but it's a place to just kind of like play with it without having to worry about changing anything inside of Node.js, which is of course depended on by millions of users every day. We don't want to take any risks with it. And so this is actually a proposal for a way to add threading primitives to Node.js. We don't know if this will work out or not. You know, this is still in the early experimentation days. But I've heard some other people talking about wanting to pursue some of these things. And so if I were to guess, there's a reasonably good chance that when Node.js 10 is landed, that we actually will probably have some kind of threading primitive in it there. But of course, it's hard to say what that looks like, and that's well into the future. So until then, we just need to remember how Node works, and specifically like how asynchronous code inside of it works. And so whenever you're debugging your applications and you see some really unexpected timing, such as, I did this code and it happened way over here, but I thought it should have happened earlier. One of the things to think about is, what is your event loop usage like? What is your thread pool usage like? And then if you can realize that, that can kind of help guide you in figuring out where your performance issues are inside of Node. All right, so if you haven't heard already, here at Microsoft we have a little survey going on. You can fill this out here and enter in a chance to win a Surface Pro. We're asking about just like, kind of what developer tools you use, kind of wanting to get to know the developer community a little better. We have a whole bunch of Microsoft folks here at Silicon Valley Code Camp. A lot of us are giving talks, some of us are just working the booth, but definitely stop by and say hi. We have a new documentation site at Microsoft as well. It's at docs.microsoft.com. This is where you can learn all about how to use Node inside of Azure and with all our other various services as well. And with that, I want to thank you all for coming. All right, we've got about 10 minutes for questions. We'll start with you in the back. Okay, so the question, let me see if I understand you correctly. Let's say you want to do a whole bunch of crypto calls, like a series of hashes on multiple inputs. Is there a way to batch those up and send those from JavaScript over to the C++ side and have them done all at once? Is that what you're asking? No, that's not a thing we have. But I would say, though, that the cost of going from JavaScript to C++ is actually very low. There's very low performance overhead to that. Just because the V8 JavaScript engine is really highly tuned these days, thanks to the browser wars that happened, about a decade ago. So there's really very little cost, or there's not much performance advantage to batching them up. You actually won't get any advantage from doing that. There's no performance difference because the fundamental limitation is the hardware. Like you can spin up more threads to try and do more work at once, but if you only have 4 cores, you only have 4 cores. So if you split it into 8 threads instead of 4, it's actually probably going to run a little bit slower than if you run it in 4 threads. The reason being that every time you spin up a thread, there's a bit of overhead. You get a communication over thread. And anytime, if you look at parallel computing, there's kind of a well-known phenomenon that if you look at performance versus number of cores, it's a curve like this. It doesn't go straight. It's like this. And this is assuming you even have the hardware to support that. Let's say you have a 32-core system, and your performance from 0 to 32 cores actually still tends to be this, because the cost of overhead of switching between all your threads gets to be larger than the work itself. But once you hit that limit of threads, all bets are off because you're gonna start flatlining right away, no matter what your work is. So you're limited by hardware, not by architecture. Any other questions? Yes, in crypto specifically, anytime you have a heavy computational workload, something where you're doing a lot of math, then yes, you're limited by the number of cores. Most modern applications, though, are not quite so CPU intensive. They tend to be I/O bound more than CPU bound. You know, they're waiting for the network or the disk or something to do something. Mm-hmm. Yes, that's correct. Yeah, so if you are doing a lot of really heavy crypto work, or just some other sort of like algorithmically intensive operation, let's say you're writing your own machine learning algorithm and you're running that locally, then those can be CPU intensive as well. So in those cases, yes, paying attention to like the number of cores you have is really, really important for the performance of your app. But only if you know that you have that kind of workload. Any other questions? Mm-hmm. Well, so the question here is like, should you use C++ or JavaScript? The answer to that is really, it depends. So like C++, you definitely do, oh, by the way, I should mention, in C++, you can write your own C++ modules and have those loaded at runtime. And like I said, the cost is pretty low, at least in comparison to other frameworks, like especially Python and Java. Using like JNI to call C++ is kind of expensive. Not so much the case in JavaScript. So you can move code over to C++. That's an option, and there's a lot of trade-offs to be involved in that. Specifically, you have to look at, well, is this an in-user application, or are you writing a library? The reason that a library is important is that maintaining a C++ module in the Node ecosystem is actually really tricky. Just because like the build infrastructure needed to build for a whole bunch of different platforms and versions and all this is big. I've actually done some work on this. I used to work, or I still work on a project called Johnny-Five, which one of the like sibling projects of that is a project called Serialport, which has C++ code. And it turns out that today, if you want to ship a module that the entire ecosystem will use, you actually have to build, I think the number right now is around 120 different variants. You have to build like 120 different binaries. And that's tricky. We're working on making that better. There's actually a really big initiative inside of Node to create a stable ABI that modules can bind to. In fact, it is actually out in the wild in the latest version of Node as of a couple days ago, so good timing. But that's only if you're running the bleeding edge version of Node, which is not most people, so you kind of have to wait on that. So what's the benefit of using Node instead of C++? Because you can write applications considerably faster. And I'm a C++ developer. Like I come from a background. I guess like C++ has a special place in my heart. But even I'll admit that like I can write an HTTP server that has like 5 RESTful endpoints and about 20 lines of code. In C++, you're looking at several hundred. So comparing Chrome to Node.js, this is a complicated comparison. So one of the reasons Node exists is that it can do a lot more things than Chrome. Specifically, we have access to the file system. We have access to all kinds of networking capabilities that we don't have in the browser. Like the capabilities are just fundamentally different. Like Node is a server-side component, and Chrome is a client, right? So they're not the same thing. The API surface is remarkably different. They use the same engine. Yeah. So they use the same engine, but if you've ever actually looked at the JavaScript spec, so V8 only implements the JavaScript spec, not the browser spec. The methods that are supplied in the JavaScript spec are actually very, very tiny. There's only, I think, like 4 global objects and maybe a few dozen methods. Like, V8 itself doesn't supply anything. It's anything useful. You can't do anything useful with just V8, application-wise, because there's no APIs that are of use. So you have to pair that engine with some set of APIs that allows to do some kind of interesting work. So the browser has one set of APIs, and that actually comes from the web spec, so it's more like, almost like the HTML side. And then Node has a completely different spec. I'm sorry, say that again? regex calls. Oh, AJAX calls, yes, yes, those are asynchronous. They have different methods. There's something kind of analogous to an event loop inside of Chrome. It works a little differently, though, and it's actually not nearly as well defined as the Node one is. Well, I'm sure it is inside Google somewhere, but it's different. It's very different. And of course, also, so AJAX calls in the browser are very limited by like cores and things like that. You can't do direct TCP calls or UDP calls from the browser. You only have HTTP or WebSockets. Whereas in Node, you also have TCP, you have UDP, and actually even some of the others as well. Mm-hmm. So this actually brings up an interesting question. This is actually not limited to just as or functions. This is anywhere in the cloud. So when you're running in the cloud, this does complicate the picture a bit because you don't have nearly as clear of an idea of the hardware that you're running on. Like, you definitely won't know if you have symmetric multithreading or not. And you may not even know exactly how many cores you have. So in a lot of these cases, the more managed infrastructures, like Azure Functions or Lambdas on AWS, you have no idea what hardware you're on, how many cores you have, how many threads are available, and whatnot. So that's actually a really complicated world where no one has good answers to this yet. The Node community is working on how we can add better instrumentation and better insight. But yeah, there's not really a great story around that yet from anyone, unfortunately. Mm-hmm. Okay, so HTTP2, yes, HTTP2 support is coming. Actually, I think it landed a couple of weeks ago. It's also very, very new. I think it's behind a flag still, although don't quote me on that. But no, there is support in Node for HTTP2. You have to be running like the absolute latest version to use it, but it is there. Any other questions? I got time for about one more. So can you use Node.js with a different JavaScript engine? The answer is actually yes. In fact, at Microsoft, we pioneered a lot of the early work around this. You can get a version of Node.js that is built on the Chakra engine instead of the V8 engine. This one is still considered beta. This is not production ready yet, but it's something you can actually get out there and use. And so you get some of the features that Edge has that V8 does not, such as like time travel debugging. And it's just a trade-off. Each engine has its pros and cons. But yeah, those two engines are currently supported. And a lot of infrastructure work going on from this initiative to make it easier to add other JavaScript engines as well. Although that's, once again, kind of peering into the future of where Node is going, not where we are right now. All right, and with that, it is 11 o'clock, and I want to thank you all for coming.